Hello everybody, my name's David, and the title of my talk is Galois Theory, You're Doing It Wrong. So what I want to talk about here is one of my favorite mathematical subjects, specifically Galois theory, and I have two goals in this talk. First, I want to make the subject accessible. I want to bring the essential ideas of the subject to a wider audience to make them more understandable and available to a wider audience. And then also I do have some challenges and questions for those of you who are more experienced in the subject. I have a somewhat different take on the whole idea, and I have some questions that have arisen that I haven't found answers to in the literature. So I have some questions as well for those of you who are more advanced in this subject. Okay, Galois theory is the study of polynomials. What's a polynomial? It's an expression involving a variable x and combined with the operations of addition, subtraction, and multiplication, and also combined with the positive integers, that is positive, negative, and zero integers, so -2, -1, 0, 1, 2, like that, continuing in both directions. So typical examples of polynomials, since we have a variable x, we can again multiply, subtract, add it together with in any combination we please with these positive, negative, and zero integers, and what we'll wind up with are expressions of the form x squared minus 5, 3x to the x cubed minus 6x plus 2, 7. A constant number is also considered a polynomial, and so forth. What we are not including here in the class of polynomials would be expressions like, so these are polynomials here. What we are not including are expressions of the form, let's just say 3 over x. That involves division, which we're not allowing here. We're simply using the three fundamental operations: addition, subtraction, multiplication. Other, actually, an expression, for example, of the form 1/4 x, actually we're not going to include. I'll talk about this a little bit more in a moment, but we're not going to have fractional numbers multiplied by x either. So we're just simply going to wind up with powers of x multiplied by integers and added together. And it's conventional to arrange the powers in decreasing order, as I've done here. So x squared minus 5, 3x cubed minus 6x plus 2. We list the highest power of x first, and then the lower powers in decreasing order. And we call this highest power the degree of the polynomial. So highest power is the degree of the polynomial. Okay. So what we typically do with these expressions is we form equations with them by setting them equal to 0. And then we try to solve for x. And this is a class of problems which has fascinated mathematicians for at least 500 years. So this is what we're going to try to explore in this set of talks. Now, let's start with a very simple example here. Okay, so we're going to start with the polynomial x squared minus 2. And we're going to form an equation by setting it equal to 0, and we're going to ask what values of x will satisfy this equation. How do we solve this? Well, you probably know from high school algebra. We move the 2 over to the other side, x squared equals 2. And we take square roots, and we get x equals square root of 2. Well, that was pretty easy, right? But have we actually solved this equation, or have we just invented a notation for the answer to the equation? Well, you may know that there are actually two square roots of 2. There's a plus and minus square root of 2. And the approximate values will be, let's just say x equals, roughly speaking, 1.414. And we'll write them x1 and x2. x2 is approximately equal to minus 1.414. Okay. But in Galois theory, we're not so much concerned with the precise numerical values of the solutions. What we want to know more about is what are the relations between these solutions, and what is the underlying structure, what is the structure of this polynomial. So, and one interesting thing we find is that if we have, if f of x is any polynomial, as we've defined it, if f of x is a polynomial, and if f of x1 equals 0, we'll write out the numbers. F of x1 equals 0. Then also f of x2 equals 0. Now this is assuming, again, this is a polynomial with integer coefficients. Remember, only allowing plus, minus, and 0 numbers to be used to form this polynomial. If f of x is a polynomial for which f of x is 0, then also f of this number is also 0. So in a way, that these two numbers are kind of like twins. You can't tell them apart, algebraically speaking. And you may say, well, what do you mean you can't tell them apart? I mean, obviously one's plus and one's minus, they're different. But the point is, from an algebraic standpoint, from a polynomial standpoint, if you have a polynomial for which one of these numbers is a solution, then the other number also has to be a solution. So in an algebraic sense, these numbers are basically identical twins. And it gets better, because if you have a two-variable polynomial, let's just say if g of xy is a 2. Now we defined a polynomial as just being an expression with one variable x and integers plus, minus, and times operations. But you can also have multivariate polynomials. This would be a polynomial in two variables, x and y, again with the same understanding that you have the operations of plus, minus, and times, and you have integer, what we call coefficients. That's what gets the numbers that get multiplied by these powers of x. So if g of xy is a two-variable polynomial, such that g of x1 and x2 is 0, then also g of x2, x1 equals 0. So these are like these numbers, algebraically speaking, they're not only indistinguishable, but they always travel everywhere together. They're like identical twins that just go everywhere together, and you can't tell them apart. If this polynomial is 0 when evaluated at x1, x2, it's also 0 when evaluated at x2, x1. So this is a quadratic equation, so this is one of the simplest possible examples of a polynomial that would be studied under the subject of Galois theory. And this might seem kind of maybe a little bit curious, but not really super interesting. However, things are going to get a lot more involved and subtle and complex when we get into third and higher degree polynomials. So that's what we're going to look at next. Okay, we can stop it there.
Okay.